The last physical applications. Now we have to talk about working with fluids. So there's going to be two problems in this set. We're going to be pumping fluids out of tanks, and then one we're going to have to talk about the hydrostatic force against the side of a vessel. So let's get into it. Here's the first one here. We have a circular swimming pool with a diameter of 24 feet. So let's draw that in. Okay, pretty big pool. It is a 5 feet high pool. Okay, so we have those parts there. And now we also know that the water is filled to a depth of 4 feet. So this light blue color here, okay, that's to a depth of 4 feet. The question is, how much work is required to pump all the water out the side of the tank? Okay, over the side of the pool. So we developed a way to do this. Okay, we're gonna first look at a little small volume here. So in this dark blue color, actually let's highlight here. In this dark blue color, we're going to consider this as a small little element of water that we're going to pump up and then sum up all those little pieces here, okay? Now, because this is a cylinder, okay, the volume is actually very easy to compute. So here we know that the radius is 12 feet, okay? And so now a little volume element here, delta V, is going to be equal to, well, the radius is 12 feet, so the volume of a cylinder is pi r squared h. So we'll have the square of our radius, which is 144, times pi, and then some thickness delta, let's call it delta y. Okay, I forgot to mention also here for this, we're going to set our 0 for coordinate system to be the top of the pool here. So the top of the pool here is y equals 0, and going down is in the plus direction. Okay, now the next step is to figure out the weight of one of these slabs of water. So it's not written here in the problem, it's a quick misprint, but we need that the weight density of water here, rho, is 62.4 pounds per cubic foot. Okay, that's the weight density of water. So to get the force here, we just multiply the volume by the weight density. And so plugging all that in, all we have to do here is just tack in a rho here. So we have 144 pi times 62.4 delta y. That's the force, that's the weight of one such element of water. Now we're going to do some work in lifting this out of the swimming pool here. So if my coordinate system has 0 at the top here, then the distance from the top to any little element of water is just y, with, of course, this remaining distance being 5 minus y. You can also set the bottom to be 0. The setup of the integral may look a little different, but the answer that you get is the same. It's just the same to a change of variable. Now then, the work required. Okay, we're just going to go ahead and jump to the integral here. So the work required to pump out all the water here, we're going to take our force and multiply it by a distance. Well, at some depth y here, okay, you have to move the slab up y feet. So we're just going to multiply our little bit above by y, okay, and we're going to integrate. So let's pull the constants out of there. So 144 pi times 62.4 times the integral of y dy. Okay, but what are our limits of integration? Well, it's filled to a depth of 4 feet, so the first topmost layer is 1 foot, okay, from the top, and then the rest is all the way down at 5 feet. So we're integrating from 1 to 5. Very straightforward application of the power rule here. So we have our constant here, 144 pi times 62.4. Okay, and I'll show it here, y squared over 2, evaluated on the boundary. And when you go ahead and do all the computations here, you should get a number that looks something like this, something about 677,498 foot-pounds of work. So that's how much work is required to empty this swimming pool that has water filled to a depth of 4 feet. Okay, so we start small, we work big, we can see the patterns here. So cylinders are very easy because the radius does not change at every level. But what if we have a different shape, say a cone? Okay, we've seen this before in the original videos here. So let's start drawing a picture. So this inverted cone has base radius 2 feet and height 10 feet. And now this time it is filled all the way to the top of water. Okay, so once again, our weight density, I'll write it down here, is 62.4 pounds per cubic foot. That's our weight density of water. Okay, and now, okay, we want to figure out how much work is required to pump all this water out of the tank. So because this is a cylinder, we have to use a slightly different way of thinking. So let me go ahead and consider well, let's first draw in like the apex, or sorry, this axis of the cone here. Okay, and let's consider another small element of water, say here. And I just want to look at, say, the corresponding radius of the slab, the corresponding distance, and then we can get everything. So we're going to have to use the principle of similar triangles, just like we did in the original video. So again, let's call this y equals 0 at the top, going down as a plus. So now let's set up the ratio, okay? We have similar triangles. Let me go ahead and outline the two triangles that we have. In red, we have this big triangle. And then in orange, we have, well, actually, I'll do it in the same color here. This color here, you have the little triangle. All right, so now let's set up our ratios. Okay, let's call this radius r. Okay, and the distance, okay, from the top to this little slab of water is y. And so this corresponding distance, the remainder, is 10 minus y. And so what are our ratios? Okay, just like before, radius of the big triangle, height of the big triangle, okay, 2 is to 10 as, okay, now radius of the small triangle, height for the small triangle, 10 minus y. Okay, that's our proportion. And now I can go ahead and cross multiply to solve for r. Once we do that, we get that 1/5 times 10 minus y is equal to r. Okay, so now I know the radius in relation to the depth at any level here. All right, so now we're going to go through the same argument here. We're going to go ahead and build our elements. So the volume of one such small element, it's just going to be, again, let's write it down, pi r squared delta y, pi r squared h delta y. Okay, well, the radius is there. When we square that, we'll get pi over 25 times 10 minus y, okay, squared, times the height, which is, well, in this case, the height is the thickness here is going to be delta y. Okay, that's our little volume element, a little puck of water. And now we think about the force, okay? And to get the force, all we have to do is just multiply the little volume element by the weight density. Okay, so we'll get 62.4 over 25 times pi. Okay, and then the rest of it, 10 minus y squared delta y. And now to get the work done in lifting this, we multiply by the distance it needs to travel. In this picture, it's y. And so now the total work done, the total work needed, is an integral. So 62.4 pi over 25 times the integral from 0 to 10, because this is full of water. Okay, the distance is y, and then the remaining part of the force function there is 10 minus y squared dy. Okay, now for the sake of time, okay, I won't go through all the steps here, okay, but you should, of course, expand. Okay, so you should expand that integrand first. Okay, you can't integrate piece by piece here yet. So when you do all the expansion here, you get y times 100 minus 20y plus y squared. Okay, now you multiply through. Okay, and now we use power rule. And in the end, we'll get a number 748.8 foot-pound. Nope, that is the wrong problem I'm looking at there. Okay, the correct number that we should have is 6534 foot-pounds. And that is the work required to lift all the water out of the tank. Okay, so same setup as before, okay, except now we just have to use similar triangles here, okay, for cones. All right, let's go ahead and look at this last one. Now we have a water trough. It's 12 feet long, and the ends are shaped like little inverted isosceles triangles, the base of which is 4 feet, and the height is 6 feet, so let's draw something like that. So across here is 4 feet, and height is 6 feet. Okay, the trough is filled with water to a depth of 3 feet, so let's go ahead and mark that in here. There's the water line. Okay, it's filled to a depth of 3 feet. Okay, we want to find the force that the water exerts on one side of the tank. Now, again, you might be thinking, well, why did I include the length of the tank to 12 feet? Well, I don't, because I only want the force on one side of this triangle thing. Okay, go ahead and look at the explanation again in the original video for that. Now, same kind of setup here, but we're going to start now, okay, by doing the similar triangle trick here. Okay, let's call this width across in blue here. Let's call that width across W. And once again, I'm going to start my coordinate system at the top here. So that's x equals 0. So this is at some distance x, maybe. Okay. And we're going to use a similar triangle idea. Okay, so let's set it up. So the width of the big triangle, 4, is to the height of the big triangle, 6, as the width at any position W divided by the height. So if we're x feet deep, that means we are 6 minus x feet from the bottom. Okay, so now we go ahead and solve for W. We get 2/3 times 6 minus x. Let's fix that there. That's equal to W. So now I have a width that corresponds to my depth. Okay. Now we're going to go ahead and go through the arguments here. We're going to first find the area of one of these little strips. We'll just approximate it by a rectangle. So this little area here, okay, well, it's rectangle, base times height. So the area, all right. So the area here will be 2/3 times 6 minus x. That's the width. And then the thickness is delta x. Okay. And now we have to think about a small force. Okay. So the way that we get this, we're going to use some of the physical laws with fluids here. Okay. Weight density times the width of a strip times the depth submerged. So all we have to do here is we multiply by the weight density, which again is 62.4 pounds per cubic foot. That's given here. Okay, times the area. So 2/3 6 minus x, and then times the submerged depth. So we have x, and then we have a delta x there. All right. And now if you multiply this through and think about it, all the units make sense here. This comes out in pounds. And so now to set up the integral, okay, the total force is going to be, so let's go ahead and pull the constants out, 62.4 times 2 over 3 times the integral from, well, we're starting at 3 feet down from the top all the way down to 6 feet because this is only filled with 3 feet of water. So the integral is from 3 to 6 of our function here, x times 6 minus x dx, okay? So again, just like normal, we go through the work, we expand the integrand here, so we have a combination of polynomials, because then we can just use the power rule. Okay, I'll show that multiplication step here because it's not too hard. If I can find my eraser, there we go. So this is the integral from 3 to 6 of, whoops, okay, integral from 3 to 6 of, multiply through, so 6x minus x squared dx. Okay, and then we use the power rule here. Okay, 3x squared minus 1/3 x cubed. Okay, and in the end, what do we get? We get a number, which you can check with your favorite calculator, something like 748.8 pounds of force on one side of the tank. Okay. So this one with the pressure, the force against the tank is a little different. We have to now work on like these little tiny rectangles acting against the surface wall of this trough here. And then we just use the principle here, weight density times thickness across times the submerged depth. And that's all there is to it here. All the topics have been reviewed now. Continue to work on reviewing these ideas, okay? The biggest thing for this is just know how to set up your integrals. A lot of these, as you saw, were just based on the power rule, okay? Especially with these physical applications. Soon, we're going to give ourselves a lot more time to develop new techniques of integration so that we can add to our toolkit. And see you in the next one.